Hey everybody, it's me again, back to teach you some calculus. Just had a long rainy practice, football, so I'm a little drenched right now. Hopefully I can dry off when I'm doing some math. And so this is the second video lesson that I've done. Hopefully it'll go a little bit smoother than last time. I'll do a little less clapping and thigh slapping than I did last time. I watched myself back a little bit and it was very annoying, so I'll try to do that. Also, I've got the hat turned backwards so that I don't obscure my face. It looked a little ominous, so hopefully I'll be a little bit more friendly today. A little bit more friendly. So today, it's a big day because as fun and exciting and as fulfilling as it is to work out derivatives with the limit definitions, today we're actually going to learn shortcut rules. Yeah, that's right, there's a shortcut. There was an easier way the whole time. That's math teacher's job. We show you the hard way first, and then we show you the easy way later. It's just our method of torture. That's why I went into the profession. But seriously, the limits form the foundation and the definition for derivatives. And what we're going to do is we're going to use the limit technique to find a pattern for certain types of functions and try to discover if there's an easier way to actually take the derivative than to go through that limiting process. And so we'll look at a few examples of that. Okay? So today we're going to look at section 3.3. We'll just do the first part of the lesson, and then the next video will show the second part of the lesson. So today our objective is to learn about something called the power rule, which is a shortcut way to differentiate polynomials and power functions, and also certain simple rational functions and square roots and things of that nature. And also we'll learn about something called the product rule, which is a very important property of derivatives. Okay? So let's get right down to it. Let's consider some situations that we already know how to find the derivative of. Through some examples from the homework problems and from examples in class, we've actually determined how to find the derivative of certain functions. Like, for example, if I were to take the derivative of a constant function, that's what this notation means. D over dx means derivative of whatever is in the brackets. So this is saying the derivative of a constant function. Well, it's just going to be 0. If you think about it, it's kind of a no-duh. If you think about a constant function's graph, the constant function's graph just does this. And remember, derivative is instantaneous rate of change, which is slope. The slope of any constant line is 0. Okay? So the derivative of any constant is 0. Another pretty easy function that we already know about is how to find the derivative of a linear function. Now, although we probably have gone through some examples with the limit definition to find the derivative of a linear function, if you think about it, the derivative of a linear function is just its slope. It's a straight line. The slope is m, so instead of going through the limit definition, if you're given a linear function, the slope is just the number in front of x. Okay? Easy enough. We've also done a couple other examples in the homework and in class lessons. We found the derivative of square root x was 1 over 2 square root x. So that's a formula that we found for this specific function. So since we know that now, I won't expect you guys to derive this from scratch. I'll just expect you to use this rule in the future. Okay? And then the other one that we also did was we found the derivative of the function 1 over x. And we found that the answer to that was negative 1 over x squared. Okay? Again, this is the general rule for the derivative at any x value, or the slope at any particular x value. Okay? So that's a constant, a linear, and a couple of specific examples of functions. But today I'm going to give you the key to differentiating all polynomials and power functions. Okay? Now, we're going to basically do this just through pattern recognition. And when I come back, I'll actually show you live a proof of why this works, for those of you guys who are a little skeptical still. But what I've been doing, other than changing diapers, cleaning up, spit up, and getting no sleep, I've actually been working with my baby on doing derivatives, showing him the limit definition, and although he's not really good at counting yet, or adding, or even opening his eyes completely, I'm still introducing him to derivatives, so I figure he's going to be a pretty smart kid. So what I did with my son Jonah is I made a list, and I put some functions down, like the function x squared. And then I went through the limit definition. The limit as h approaches 0 definition, or you could use the limit as x approaches a definition. Both of them work equally as well. But I found that the derivative function for x squared was the function 2x. Okay? Similarly, I did the function 3x squared, and the derivative for that turned out to be 6x. Now I'm trying to establish a pattern here. So as I do these examples, I want you to think about, wonder if there's some way we can go directly from here to here without going through the limit definition. Okay, now if you already got it, keep it to yourself, because if you say it out loud, you're going to spoil somebody else's sense of discovery. Okay? So just keep it to yourself right now, keep it on the low, wait for it. Here's some more examples. 2x squared minus 13x plus 5. If you go through the limit definition to find the derivative, it turns out the derivative of that is 4x minus 13. Have it yet? No, don't say it. X cubed. The derivative of that turns out to be 3x squared. I got all these with the limit definition. Let's do some more. I did the function x squared plus x. Derivative? You think you know it? Write it down on a piece of paper if you know it. See if you test your knowledge here. Derivative, 2x plus 1. If you got that, you might know the rule. Let's see. Let's do another one. 5x to the fourth minus 2x squared plus 6. If you think you know, write down the derivative of that. Turns out the derivative is 20 x cubed minus 4x, and that's it. How about this one? Yeah, I'm giving more examples. You might know it already, but some people are a little bit slower, and that's okay. So just give them a little bit of time. A couple more examples, and we'll figure out a pattern and write down a rule for it. All right, 8x to the 10th minus 7x to the 5th. If you think you know, write it down to impress your friends. Turns out the derivative is 80 x to the 9th minus 35 x to the 4th. If you got that, you probably understand the pattern. But how about this? Oh, the function 1 over x cubed. Not so smart, are you? Can you do that one? What if you rewrite that as a power function? What if you rewrote this as x to the negative 3, which means the same thing? You think you know? Derivative of that is negative 3x to the negative 4 power. Okay? So look at, if you look back at all these examples, notice that basically what's happening here, and here's the spoiler, is that you're taking the exponent and you're multiplying it by the coefficient in front, like 2 times 3 is 6, and then you're lowering the power of the exponent by 1. And if there's more than one term, you just do that with each term. Okay? So going down to here, some of these more